Section 33.4 Comparative Values for Speed Distributions. The probability density function of the three-dimensional speed v is complicated. It's this. This part is the product of the probability density functions in the x, y, and z directions. And then you have 4 pi v squared. This is the surface area of a sphere with the radius v. And again, vx, vy, vz are the three components of v. We can verify that this is the correct function by integrating this with respect to v from 0 to infinity. And this integral is 1. That makes sense. The gas particles have to move at a speed between 0 and infinity, 100%. Now, how can we maximize the probability density function, this function, and get the most probable speed? It's very simple. To maximize or minimize a function with respect to a variable, you simply take its derivative with respect to that variable and set it to 0. So we just need to solve this equation. How do we solve this equation? We first plug in the expression in here. Well, this is complicated. Just plug it in. The nice thing about this function is we do not have to worry about the constant part. For example, this part does not depend on v, and this 4 pi does not depend on v. So we can already simplify this equation to here. And then we use the product rule. We take the first derivative of v squared, that's 2v, multiplied by this Gaussian function. And then we have v squared times the first derivative of this Gaussian function. You have to use the chain rule here. And then we simplify this equation. We get this one by dividing both sides by e to the power of negative mv squared over 2kbt. We have this. All right. And then we have this simplified equation that leads to the most probable speed. It's simply the square root of 2kbt over m, or the square root of 2rt over m. Again, this is because r is kb times the Boltzmann constant. The molar mass is the mass of one particle times the Avogadro constant. Now let's use this equation for helium and argon at the room temperature. The most probable speed of helium is simply the square root of 2RT over the molar mass of helium, 0.004 kilogram per mole. You get 1100 meters per second. For argon, you have a larger molar mass, therefore you have a smaller most probable speed, 350. So let's look at the speed distribution of helium and argon. Let's see if they are maximized at 1100 and 350. Over here, 1100. This is for helium. For argon, this is the green line. 350. So at 350, the probability density for argon is maximized. At 1100, the probability density is maximized for helium. Now, neon is between helium and argon. What about xenon? Well, xenon atoms move slower than argon. We know the average velocity is 0 in the x direction, in the y direction, in the z direction. Therefore, the average velocity in 3 dimensions is also 0? Well, because its x, y, and z components are all 0. But can we find the average speed? Is that 0? Of course it's not. You think of a bunch of gas particles. They all move at a positive speed, so the average speed cannot be 0. But how can we find the average speed? Well, it's very simple. You have this part as the probability of finding a particle moving at a speed between v and v plus dv. And then this is the speed v. So really, over here, it's the probability weighted speed. And we integrate this from 0 to infinity. We'll get the whole range for the speed. Now we plug in the expression for this f. It's here, and then 4 pi v squared over there, and then we integrate this. All right, so the difficult part is we'll have to integrate this Gaussian function, but it's not too difficult. So first, we move things around to simplify this expression, because v times dv is half dv squared. So that's why you see a dv squared here. All right, this is dv squared. And you see the half over there. All right, so this is the first move we did. And then we set q to be negative mv squared over 2 kBt. This is variable substitution. All right, so in this case, we change this part. We simplified this Gaussian function to a simple exponential function. Again, over here, this part becomes e to the power of q. So that's very simple. All right, by using this variable substitution. And then v squared can also be expressed in terms of q, right? So now we replace v squared with q. So this 4 pi v squared is 4 pi, okay, this part is your q. And v squared, okay, that becomes q times this constant. Again, this is just variable substitution. All right, now let's look at the lower and upper limit. So q is negative mv squared over 2 kBt. So when v is 0, q is 0. When v is infinity, q is negative infinity. All right, so that's why we changed the upper limit to negative infinity. Now we just need to integrate this. First, we take all constants out of the integral. So you have 4 pi and 1/2, it becomes 2 pi. And then we copy this to here, and then we have this 2 kBt over m over here, another 2 kBt over m, put it in here. We have negative sign here, another negative sign here, they cancel. All right, so really we just need to integrate this e to the power q times q. All right, so that's easy. The integral of this is q times eq minus e to the power of q. All right, and then we plug in the lower limit, upper limit. When we plug in this negative infinity to here and to here, we get 0 minus 0. And then we plug in q equals 0. When q is 0, this part is 0, and over here we have a negative 1. So this integral is 0 minus negative 1. That's positive 1. All right, that's positive 1. So we have this 2 here. We copy this 2 here. We have this pi. But then we have this 1 over pi to the power of 3/2. So we combine this 2 to get this. And we copy this to here. And finally, we put everything together. We get this 8 kBt over pi m to the power of 1/2. Let's compare this average speed with the root mean squared speed. All right, the average speed is a little smaller than the root mean squared speed because 8 over pi is roughly 2.55. That's smaller than 3. In general, if you have just any set of data points, as long as they're real numbers, the root mean squared value is always greater than the average value. So you can see here, the root mean speed is greater than the average speed, but you can say this more generally. The root mean squared value is always greater than the average value of real numbers. Why is that? Let me give you a simple example. Let's say we have only three numbers, 1, 2, and 3. The average, of course, is just 2. What about the root mean squared value? Well, in this case, you need to take the square root of the sum of 1 squared and 2 squared and 3 squared over 3. The result is 2.16. It's greater than 2. So how come this number is greater than the average? Well, it's very simple. Now you can see the first number 1 is multiplied by 1. The second number 2 is multiplied by 2. The third number 3 is multiplied by 3. Right? So we actually put more weight on larger numbers. So that's the reason. That's why the root mean squared value is always greater than the average. And actually, mathematically, you can always prove this rigorously. All right? The RMS value is greater than the average value. The equal sign holds true only if all data are exactly the same. So in summary, we have the root mean squared speed. All right, it's here. We have the average speed. It's here. And we have the most probable speed. It's here. They have a common factor. The common factor is the square root of kBt over m. Square root of kBt over m. Square root of kBt over m. The only difference is the number. Over here you have the square root of 3, the square root of 2.55, the square root of 2. So that's the only difference. In case you need to calculate the root mean squared, average, and most probable speed, it's more convenient to pre-calculate the square root of kBt over m first, and then multiply this by the square root of 3, the square root of 2.55, and the square root of 2.